The class video for Friday, October 2nd, 2020, and I'm going to go over the opener. So this is Q10. This is from the 1.7 questions that you did in class today. And it asks, how can we explain the trend of increasing ionization energy as we remove successive electrons? So first of all, we need to know what the trend is before we can start explaining it. As we go across the periodic table from left to right, we know that ionization energy increases. They're telling us the trend. Now we have to explain it. So there are two things going on. First of all, the effective nuclear charge, or Z effective, okay, Z effective, is increasing. We are adding protons as we go across. Okay, so more protons in the nucleus means more attractive force. All right, secondly, we are adding electrons to the same, to the, got two thes there, to the same shell of electrons, to the same shell of the atom. Okay, we're not going out to a different shell, so the distance from the nucleus is relatively fixed, is about the same. All right, because of these two things, as we move from left to right, for each element as we go right, the nuclear charge increases, but we're adding electrons into the same shell, so that distance between the nucleus and the outermost shell, if this is our valence shell and this is the nucleus, this positive nucleus, that's not changing, right? So nuclear charge is changing. This distance remains fixed. There's more attractive force. Therefore, as we go across, it's harder and harder to pull this electron out of the valence shell. All right, so hopefully that makes sense. Now, the next question asks, why is the second ionization energy of sodium so much larger than the first ionization energy? So let's take a look at what that actually means. What's the difference between the second ionization energy and the first ionization energy? So for sodium, okay, remember sodium is number 11 on the periodic table, so it has 11 electrons, 11 protons, okay? We're not going to concern ourselves with the neutrons because these are the charged particles. For the first ionization energy, okay, we're going to have sodium, gaseous atom. We'll lose an electron. So that means if we lose an electron, it becomes positively charged plus one electron. Okay, so that's the process for the first ionization energy. The second ionization energy, we now take a second electron away from sodium. So here we have sodium plus gas. Now, if we take a second electron off of something that's a plus, we now have sodium 2 plus gas plus another electron that flies off. So that's our first ionization energy, going from the atom to a +1 ion. And here's our second ionization energy, going from the +1 ion to a +2 ion. In each case, one electron gets removed. So it's harder to remove this second electron right here, because if we look at the pictures of sodium and sodium plus, here's sodium gas. We got our +11 nucleus, We've got our 1s electrons as usual. We've got our 2s2, 2p6 electrons as usual. And then in the outermost shell, we have our 3s1 valence electron. So for the first ionization energy, we're losing that valence electron. Okay, this guy is going to pop off, okay, and leave as our electron. And then we'll be left with the core electrons, which look just like neon, okay, once it leaves. This looks like neon, a noble gas. So sodium atom readily gives up its valence electrons so that it can look like neon and have that closed outer shell. On the other hand, you're taking Na plus, which, okay, it looks like neon. Okay, and we're gonna try to force it to, we're gonna take another electron off. So we're taking something that looks like neon, has a closed outer shell, and we're trying to take a electron off of here, right? Na plus, okay, looks like this. It has the plus 11 nucleus still, but it has our 1s2, then our 2s2, 2p6 completely closed, and you attempt to take off an electron from this full outer shell. Guess what? Sodium plus does not want to do that. So this second ionization energy is much, much larger than the first ionization energy. Okay, so much, much larger because we are attempting to remove from a closed outer shell, or full, rather, full outer shell. Oh, my handwriting's getting very bad. Should try to get that a little bit better. Okay, so hopefully that makes sense to you now. Okay, we talked about some survey feedback and decided that answer keys, best way to post would be to public comment on the assignment. We talked about, you know, what we're seeing on AP Classroom, so on, and we decided that unit test 1 will be A week Monday class 2, but it turns out next A week Monday we have Indigenous Peoples Day. So our test will not be on Monday, but it will be on Tuesday, 10:13, in the second half of we'll have like a you know, half an hour in class 2, and then we'll take the exam. Okay, so let me change my pen again, get it a little thinner. Okay, so just the format for unit test 1, the Flipgrid is going to count as 20 points of the test grade. Then we have 50 points for the FRQs and then 30 points for the MCQs. Exactly how I'm going to put those, I'm not sure. I may actually use Edulastic. It seemed to work well. Okay, so an overview of the trends. So you cannot explain a trend by saying ionization energy increases or atomic radius decreases. That is not an explanation, okay? You can't say, oh, I know fluorine's ionization energy is larger than the ionization of energy of oxygen because ionization energy increases when we go to the right. That's not an acceptable explanation. That just tells me that you memorized the trend, which you should. You should definitely memorize the trends, but you can't use them to explain why something is bigger than the other or something has a higher ionization energy, etc. Okay, so let's review the trends here. So atomic radius from first we'll do left to right. So atomic radius will decrease. Okay. Ionization energy of atomic radius is decreasing. Those electrons are getting closer to the nucleus. Ionization energy increases due to higher attractive forces between the electrons and the nucleus. Electronegativity, as we go to the right, it increases. Okay. Electronegativity, again, is the tendency of atoms to pull electrons towards itself when bonded. Okay. Applies to bonded atoms. And the most electronegative element is fluorine. Metallic character, as you can see, as we go across, we become more and more non-metallic. So metallic character decreases and non-metallic character increases. And these things all will affect the reactivity of your element. Okay, now going down a group, atomic radius increases. The simplest explanation for this is that we are going down a group, and each period we add a shell, an energy level of electrons. However, as we go down, the shielding, okay, increases by one shell too. So the effective nuclear charge is not changing. It's pretty much constant as we go down. However, we're adding a completely extra shell of electrons, so the atomic radius increases. The ionization energy, again, with a larger atom with more electrons, your increasing atomic radius, right, means that there's less attractive force between the valence electrons and the nucleus. So ionization energy decreases. Electronegativity decreases. We're getting further away from our fluorine. Our metallic character increases, and our non-metallic character decreases. So that's the trends. Now, explaining the trends, right, we want to use these concepts. Doesn't mean that you have to use all of them for every question that you answer, but these are the tools, the concepts that you'll use to explain why something is larger than the other, why something has a higher ionization energy, okay, why something might want to gain an electron as opposed to lose an electron. So these are all different concepts that you can use to explain these trends. All right, so couple of questions. First, ionization energy of carbon, higher, lower, the same as silicon. So we're going down the group here. And in a group, the ionization energy decreases. Okay, so the first ionization energy of carbon is going to be higher, okay, than the first ionization energy of silicon. Okay, remember, we're adding that whole shell of electrons as we go down. So it's gonna the electrons will be further from the nucleus and easier to remove as we go down. That's why ionization energy decreases. Is the first ionization energy of carbon higher, lower, the same as nitrogen? Well, now we're going from left to right. Our ionization energy increases. So the first ionization energy of carbon, okay, is going to be lower than that of nitrogen. As we go across, we get an extra proton here in nitrogen. The nuclear charge is increasing. Therefore, it will attract the valence electrons more and make them harder to remove from the nitrogen atom. Which ionization energy will be larger? The first ionization of Mg or the second ionization energy of Mg. So let's just write down these processes again as practice. So ionization energy number 1, this is going to be Mg, gaseous atom, okay, turns into Mg plus gaseous atom plus an electron, okay. Ionization energy 2 is Mg, gaseous atom, okay, sorry, Mg plus gaseous ion. Okay, remember, second ionization energy, we got to start with the ion here. And then we go to Mg2 plus gaseous ion plus an electron flying off. Okay, so which will be larger? Well, this first one we're going to remove, but as we remove that first valence electron, okay, we now have one valence electron left in the valence shell of magnesium, but there's less repulsion now, okay, less electrons for the plus 12 nucleus to attract. Okay, so the attraction grows. This ionization energy is going to be larger. Okay, and in general, that will always be true. It'll be successively harder and harder to remove electrons because this plus 12 nucleus now has less and less electrons to remove, to attract. Okay, and here's just an explanation in terms of Coulomb's law. Okay, this positive charge is staying the same. Okay, our negative charge of the electron is staying the same. Okay, but we're reducing the repulsion between the valence electrons by removing one. And so this will allow the nucleus to pull in that single electron better, okay, making it harder to remove that second electron from the valence shell. I don't know about scooching. I think it's more sort of like a kind of a pulling in effect. So as we can see, we know that going from I1, and this is like IE1, IE2, so on and so forth. We know that the second ionization will be greater than the first, and the third will be greater than the second, so on and so forth. But we can also see this pattern of a sudden jump or leap in the ionization energy when we've finished removing the valence electrons. So in sodium, okay, we have one, oh, looks like I can't write over there. So we have one valence electron in sodium. So there's that first ionization energy is losing the one valence electron. Now we have to go into the core electrons. Okay, so the ionization energy, right? Look at the second one. It's like 10 times the ionization energy of the first electron being removed. Huge jump. Okay, now with Mg, we've got two valence electrons. All right, so we remove the first, 738. We remove the second, 1450, and then big jump. Okay, we're going up by about 6, 7 times, right? Because again here, this is removing a core electron. Okay, how about aluminum? Does this pattern hold? So aluminum has 3 valence electrons. Remember the pattern from the periodic table. So we remove the first, we remove the second valence electron, we remove the third valence electrons, and then boom, big leap, about 5 times greater in ionization energy. Whereas you can see like the difference here, 578 to 1820, maybe about 3 times. This is less than doubling here, and then 5 times. Here in Mg, right, we got 738, then it doubles, but then from here to here, about 5 or 6 or 7 times right here. Okay, so whenever we break into those core electrons, we're getting this leap, this jump in ionization energy between after we remove the valence electrons. And AJ asked a nice question, do these exist, or like why are these blank? They certainly do exist. You can get tables for the ionization energies. And I think basically they were just trying to illustrate the point that, okay, we're removing a core electron here, and these get higher and higher and higher. But what we want to show here is that Once we remove the valence electrons, we see a big jump in the ionization energy, the next one, because we're breaking into the core. All right, so here is a similar problem. Why is lithium's second ionization energy so much larger than the first, but beryllium's third ionization energy is so much larger than the second? So again, Bohr diagrams are helpful, or the Bohr model can help you think about this. So here, let's look at lithium first. So lithium, the first ionization energy, okay, we're going to go from lithium atom to lithium plus, and you should be thinking right now, oh, I know this is going to look a lot like sodium. And you're right. So then we take lithium plus ion and we go to lithium plus 2 ion plus an electron. So again here, now lithium ion looks like helium. Okay, so we're breaking into this closed shell of 2 electrons. It's going to be very hard to remove them. So we get a big jump in the ionization energy between IE1 and IE2. Okay, so that's why the second one is so much larger than the first for lithium. However, for beryllium, okay, we've got to write out 3 ionizations. So we got Be gaseous atom going to Be plus, okay, plus E minus, and then we have IE2 plus gaseous ion going to Be2 plus an electron, and then we have IE3 Be2 plus gaseous ion going to Be3 plus gaseous ion plus an electron. So we're removing 1, 2, 3 electrons. So for this one, I am going to draw the Bohr model for you. I would say draw out the Bohr models for lithium if you're not seeing this. But for beryllium, okay, beryllium atom, we have a +4 nucleus. We've got the 1s2, and we have 2s2 here, okay? So the first one, we're removing that, and we're changing into something with a +4 nucleus, 1s2. Try to draw this a tiny bit smaller, 2s1, okay? All right, so remember, beryllium had 2 valence electrons, and now these are the core, the 1s. Let me use a different color here. Our core will make red. Okay, so we've got our 2 core electrons, and our black dots are our valence electrons. So this first thing, this process here is IE1. Okay, so we got IE1 happening here, and we have an electron that flies off. Okay, all right. What about IE2? Now we're taking our +1 beryllium, and we're going to, we still have our +4 nucleus here. We have our 1s2 electrons, but guess what? We've got no 2s electrons. All we have left are the core electrons, okay? So here, again, we go this way, and we lose 1 electron, flies off. Okay, that was our IE2. All right, so now to do IE number 3, okay, we go, my arrows are going to go west at this point. Okay, so here we have +4, and we've got to remove one of these core electrons. These core electrons are feeling the full force of this +4 nucleus. Okay, so I'm going to remove that core electron, it's not going to be easy to do. Okay, so here we got our electron flying off. Okay, so now, right, we have to remove that core electron. Okay, right here, IE3 is a big, gotta get some more paper here, big jump, okay, because we're removing from the core electrons, which feel the full force of the +4 nucleus. Okay, so that's why there's that big jump between the second ionization and the third ionization for beryllium. Okay, so here's again an explanation for this. Okay, a little shorter. Now we go to this example. Is the first ionization energy of oxygen larger, smaller, or the same as nitrogen? Again, we would expect, okay, going across, our trend says that ionization energy increases. So we expect the ionization energy of oxygen to be greater. But no, unfortunately, there are always exceptions, but this is due to the properties of these atoms, okay? The ionization energy of oxygen is lower than for nitrogen. Okay, so nobody's expecting you to know these exceptions, but we're expecting you to be able to explain these exceptions. So if we take a look here, okay, the trend makes you think that oxygen should have a higher ionization energy. But however, the data shows that the ionization energy of oxygen is actually lower. Okay, so what's going on here? Well, we happen to have, okay, in our oxygen, I'm going to redraw these because this is some archaic orbital notation that you've probably never seen. So for nitrogen here, we've got 1, 2, 3. We're just going to draw the 2p subshell. All right, so for nitrogen 2p, we got 1, 2, 3 up arrows. For oxygen here, we got 1, 2, 3, 1, 2, 3 orbitals, but we have 4 electrons in the 2p. So we got 2p3 and 2p4. When you put that paired electron into one of these 2p orbitals, okay, remember the 2p orbitals look kind of like this. Oh no, our orbital's blue. Maybe we'll make them blue. Okay, so normally, okay, we can kind of imagine there are 2 electrons in that one orbital. Guess what? 2 electrons, I guess you can't really see those 2 electrons. 2 electrons in the same orbital are going to repel each other. When they repel each other, this causes something called repulsion energy. It causes repulsion. It increases the energy of that orbital. Okay, makes it a little less stable because it increases the energy. Therefore, there's this repulsion energy there that is not present in nitrogen. So when we take one of these electrons and remove it, we are actually, okay, we're taking away that repulsion energy. So it's kind of a compensation. So we're going to remove our electron, and it takes energy to do that. But because there's this repulsion energy, okay, that's increasing the energy of the orbitals, it actually causes the ionization energy to go down. Okay, so because we're losing that repulsion energy here. In the nitrogen atom, there is no repulsion energy. We just kind of take one away. Okay, so this is why we see this lowering of ionization energy. Okay, because this repulsion energy can't be compensated by the increased nuclear charge. And then you're right, we see that kind of pattern with phosphorus and sulfur, arsenic and selenium. There's another place where you see it, but this is kind of the most common place where you see this trend. Um, you will see in between group, we have group 2, 1, 2, between group 2 and 13, you also see a little bit of this lowering due to this closed shell of the S's, but don't worry about that. This is kind of the exception that comes up once in a while on the AP exam. Okay, going on here. 1.8. Okay, so that kind of ends 1.7, which is on periodic trends, and then 1.8 we're going to just touch on very briefly in this unit, because in unit 2 we're going to be using this all the time and talking about the compounds. So just remember, valence electrons are the ones in the outermost shell. The rest are called core electrons. So these valence electrons are the reactive ones. They are what cause chemical reactivity between different elements. And valence electrons, there's this clear pattern of valence electrons for the main group, okay? These are called the main group elements, groups 1 and 2, and groups 13 through 18. Okay, these together make up the main group elements. All right, so we see that pattern, and we can also see that there's a pattern in the metallic character of elements. So we've got our nonmetals in the kind of the upper right. We've got our metalloids along the stair-step line. All the things to the left are metals. So one thing to note is that our atomic structure, all the stuff that we've been talking about, will determine the metallic character and the reactivity of an element, how likely they are to lose or gain electrons. Metals tend to lose electrons. They tend to form cations. So you can see all these cations over here. Nonmetals tend to form anions. And notice that hydrogen is kind of a ambivalent case, can do both, ambidextrous, okay, lose and gain. Okay, it's more common for hydrogen to lose electrons, but it can also gain electrons when paired with an active metal. And this does not mean that these are the only charges for these elements. These are the most common charges for the elements. For example, we can have positive charges for some of these nonmetals, and so that's just something to keep in mind, but that these are the most common charges. The other thing is with noble gases, xenon, okay, forms compounds. Doesn't say that here, it doesn't give any charge, it generally forms molecular compounds, okay, molecular. So that's if they say noble gases, they never react, well, it's actually not true. Okay, so when we get down to xenon, their electron clouds get a little bit more squishy and squishy, and are they're willing to share those electrons. Okay, so last slide, again here, this pattern of valence electrons. Just be careful, this is group 18, so let me go and fill in those ones. This is a more common group number, but just remember this is helium, okay? Helium has 2 valence electrons, okay? Helium has 2 valence electrons because it only has a 1s2 shell. Okay, so if we have this pattern in valence electrons, that means that elements in the same group, in the same family, will react the same way, and they will form similar compounds. Okay, so there's going to be a very similar pattern in the compounds that are formed between elements in the same groups. So here we have sodium, group 1, chlorine in group 17. Sodium will form an Na plus. Okay, remember all of group 1 forms +2 cations, all of group 2 forms +2. Okay, group 13 is +3. 14 is variable. Okay, then we have 15, -3, -2, -1. Okay, so if we have sodium plus and chlorine minus in our ionic compounds, we have a metal and a non-metal. They form an ionic compound. We will get NaCl. And I will just balance that. Okay, got to change that. Okay, so an element that would react similarly to Na is anything in group 1. So here we go, lithium. Okay, so lithium plus chlorine, similar reactivity. It will form LiCl because all Li also forms a +1 cation. And then the reaction will be balanced the same way. They will react in the same proportion. Okay, K and Br. K is in the same group as Na and Li. Br is in the same group as KCl. Guess what? They are going to form an ionic compound that also has a 1-to-1 ratio of the ions. And our coefficients to balance will be exactly the same for this reaction. Okay, an element that behaves similarly to Br, iodine. Okay, so if we add potassium to iodine, we get, again, a formula for the ionic compound, which is a 1-to-1 ratio of the ions, and it's balanced the same way. All right, now Mg is not in the same group as Na, Li, and K. It will not behave the same way with the halogens. We will not get a similar formula as the halogens with the alkali metals with group 1 and group 17. Now we have group 2 with group 17. Mg is right here, okay? You've got Mg right here. It's in group 2. It will make a +2 cation in an ionic compound. It will combine with Cl minus. We've got to have 2 Cl minuses, okay, to balance out the +2. Okay, now we get a different ratio of the ions and different balancing, right? It's just 1, 1, 1. What would act similarly to Mg? Well, right below it is calcium. Okay, so calcium plus Cl2, we are going to get an ionic compound with exactly the same ratio of ions, 1 to 2. 1 positive to 2 negative ions. Okay, let me fill in also here are Li and A and K, and it might help for you to know that over here we have F, Cl, Br, and I. Might as well fill in these other guys here. Okay, so that ends 1.8, and hopefully this sort of pattern will help you, and we will definitely talk a lot more about compound formation and forming molecules in Unit 2. Okay, that's it.